Welcome back after break. I know it's a long way. Well done for making it back. So this is the second session of PEPM'26, and we have 4 talks. And the first one is going to be given by Harbo, who is going to tell us about computation-tree semantics.
So yes, thank you very much for the introduction. So in this joint work between myself, Sean, and my PhD supervisor, Hans Hüttel, we have been developing a new approach to describing inference rules, which we call computation-tree semantics, and wherein we capture the algorithmic aspects of these structural inference rules. So when we define the semantics of a programming language, we commonly do this using what is called an operational semantics. And these come in 2 styles. There's the big step style, or also called a natural semantics after Kahn, and there is the small step style, also called a structural operational semantics after Plotkin. Each of these have their own advantages that stem from one fundamental key difference. The first being that big step rules, as you see over here, describe one complete computation in one step, so to say, whereas small step rules over here describe a single computational step in a bigger computation. As a consequence, the big step rules are often less numerous and also slightly simpler compared to the small step counterparts. But the small step rules have an easier time describing certain features or program features such as non-termination or parallelism. Another advantage of the big step rules is that they are more resemblant of how someone would implement an interpreter, so using a big step semantics gives a more natural transition from specification to implementation. Due to their distinct advantages, there has been a lot of work on reconciling the two styles by deriving one style from the other. In this line of work, we typically see the big step to small step conversion as the more challenging direction, and this is also what we've been working with in this work. So we've studied a range of previous works working with this big step to small step conversion, and some of them use very similar, some very different approaches, but there is still one key thing they all have in common, and that is, first, they use the premises of big step rules to break the big step semantics down into small step rules, and then we chain these small step rules together by some notion of memorization. And some typical approaches we see here is to use a stack of continuations or a continuation passing style to do this memorization. With computation-tree semantics, however, we take a slightly different approach and try to capture as much as possible of both the big and small step aspects of a semantics as possible, thus giving us the best of both worlds, but without the need for converting from one style to the other. The core enabling data structure that allows us to do this is the computation tree. And you can see 2 examples of computation trees right down here in one full example of a step in computation tree semantics. So as you can see, steps go between these computation trees, in contrast to a normal small step semantics where the configurations are flat, so to say. So one key property of these computation trees is that they directly encode both evaluation contexts and continuations. And in the example down here, we can, for example, see that the expression 1 plus 3 plus x is being evaluated in the context of sigma, and we're currently memorizing the value 1, which was established at a previous step when evaluating the first constituent 1, seen out to the left. Now, 1 plus x plus 3 has itself gotten to the point of evaluating x plus 3, the left constituent, and x plus 3 is again evaluated in the context of sigma, and we're memorizing the value 2, which will have been established again in a previous step when evaluating x. Finally, x plus 3, as seen in the top, has gotten to the point of evaluating the second constituent 3, and it is being evaluated in the context of sigma, but we have not yet established the value of that literal 3. So this is where we start to see continuations, because the only way to progress from here is to continue the evaluation of 3, because the 2 previous nodes in the tree are still waiting for the sub-computations or sub-goals to be completed. Thus, in one step, we can establish the value 3 of the literal 3. And after this, the annotations such as add2 down here tell us what to do with the values of sub-computations. For example, for addition to proceed, we'll have to add 3 and 2 together, but you'll see this shortly. So another important feature of these computation trees is that they preserve the full unchanged syntax of whatever program or expression is being evaluated. And you can always, by looking at the root, see that complete syntax. And this plays 3 key roles. First, it gives the computation tree a structure that is similar to big step derivations, as you will see later, and is important for capturing the big step aspect of a semantics. Next, since we always have the full syntax, we know exactly which parts of the expression or program is being evaluated, and this helps us capture the algorithmic aspects of a semantics. Finally, by using these computation trees, we can capture the small step aspect of a semantics, as you could see here in a stepwise restructuring of this tree, but at the same time, we can actually describe this behavior using rules that follow a mostly big step-like structure, as seen right over here. So to see how these rules work, let's try to evaluate a simple expression x plus y. So the addition rule, perhaps it would be easier if I just point with the cursor. Would that be better? I'll just do that. So over here, the rule states that to evaluate any E1 plus E2, we must start out with a computation tree node that contains a sigma in what we call the primary component and the empty secondary component. And here it's probably easier to just point. That is also what we see up here with CT1. X plus y is evaluated in the context of sigma. So next we proceed by matching the secondary component from the current computation tree, which is CT1 currently, with the patterns that you can see right down here with add1 and add2. So these are clauses, and since the secondary component is empty and add1 has the empty pattern, add1 is enabled. So to proceed from here, add1 tells us that we need to evaluate E1 given the state sigma to some value n1, and this implicitly happens in one or more steps. So initially, to initiate the evaluation of add1, then we grow the computation tree into the constituent up here corresponding to E1, which is x in this case. And then that concludes the entire initial step for add1. Next, we can then use the variable rule, which you see down in the corner, to state that x can evaluate to some value n1 by a simple lookup in sigma. Now that we have established the value n1 of x, that is the same as having established the value n1 here in the addition clause. So the way we then proceed is to update the primary component, as seen over here, to the same sigma, but update the secondary component to store n1, the value we just found, and that is what we see in computation tree 4. Now we can evaluate y in a very similar manner. We grow the tree into y, we establish the value n2, and then, as per the rule add2, right, sorry, I forgot to mention, now that the secondary component contains n1, we have enabled add2 because n1, it now matches the pattern in add2, and therefore we can evaluate E2 to N2 and produce the final result N1 plus N2, as we see here with computation tree 7. So now that you have seen how these rules work, we can also observe the correspondence between a big step derivation and an equivalent CTS transition sequence. So here we have the same transition sequence and an equivalent big step derivation. And in the root of the derivation, we can see that x plus y is evaluated in the context of sigma, and that is what we see in CT1. Furthermore, the root node over here says that x plus y evaluates to n1 plus n2, and that is what we see in the last computation tree down here. Now, these the subsequences for evaluating x and y then follow a similar pattern where we have two corresponding computation trees for every big step derivation tree node. Furthermore, we have a similar nesting structure, so to say, where here we can see that x is the child of x plus y in a similar way as x is a child of x plus y right over here. And this becomes important later. So an easy way to see how this works is to see the computation trees as partial big step derivations, where the computation tree essentially grows up through the big step derivation until we establish the value of some constituent, and then we pull that value down towards the root. So n1 is pulled down, and then n2 is pulled down, and when everything goes to the root, we have the final result. So now that we have seen this correspondence, we can also start looking at the conversion from big step rules to computation tree semantics rules, or CTS rules. And here we use a similar approach as to previous works, where we essentially take the premises of a big step rule and then turn them into their own clauses in a corresponding CTS rule. Furthermore, the left-hand side of the conclusion becomes the rule head, as it's called, and the right-hand side becomes the terminal result of one of the clauses, in this case the second clause. Finally, we use the secondary component to store the value n1 of e1 so that it is remembered at a later point in time. So this is just this is just part of one example that we have in the full article, where you can see the full conversion and also see a full equivalence proof that proves that these two are in fact equivalent. But I'll show you an example of that later. Furthermore, an important thing to note is that whereas CTS imposes a strict evaluation order, E1 first, E2 afterwards, then this order is not actually imposed in the big step rule. And therefore, we could easily also have created a CTS rule where E2 was evaluated first. But here we just picked to evaluate E1 first. Now, going up to a slightly more complex example, we also cover an example where we transform Launchbury's big step semantics for the call by need lambda-calculus into an equivalent computation-tree semantics. And here we see an example conversion for the application rule. We follow a similar pattern to before. Each of the big step premises become a clause in their own clause in the CTS rule, and the conclusion becomes the header and the final result, and so on. But here it's important to note that the heap gamma, which shows up over in the big step rule here, is updated to delta throughout the evaluation of that rule, and that must be mirrored in the CTS rule. So first, when we evaluate, the header up here, gamma, always refers to the primary component of the current CT node, or the current computation tree node that we're looking at. So initially, gamma up here will correspond to the gamma from the big step rule. And when we evaluate app1, then gamma up here corresponds to the big step gamma. Now we produce an updated delta and store that delta in the primary component along with the value set, which means in the next step after that, gamma from the rule header will now correspond to delta from the big step rule. And thus, when we evaluate E prime over here in gamma, that is the same as evaluating in the context of delta from the big step rule. And then everything just follows in the same way as before. Again, you can see the full conversion and full equivalence proof in the article, but I'll show a small piece of the equivalence rule for the lambda-calculus later. Finally, for the third example that we also covered in the article, we have a semantics for the while language, and here we also see the example conversion for the while rules. So again, the primary components essentially become their own clauses in the corresponding CTS rule, and we thread the updated primary component through the rules, as with the previous two examples. However, now, since we have two judgments over here for evaluating the loop condition, and these are essentially equivalent, we can just put one instance of that judgment in the CTS rule and use the secondary values to match on whether we're following the false or true branch. If the condition evaluated to false, we just output whatever sigma that we currently have, but if it evaluates to true, then we can evaluate the while body. Now, after evaluating the body, we update the primary component and go back to the empty secondary component. And this is interesting, because this re-enables while e, which means we can again evaluate the loop condition and possibly also the loop body, thus giving us an iterative behavior which is actually described fully compositionally in the program syntax, which is not actually possible in either big step semantics or a small step semantics. Now, moving on to how we prove equivalence. Here we can use the correspondence between a big step derivation and computation trees that we saw in a previous slide. And yes, as mentioned, you can see the full examples in the article, but here I'll just show you a small part of the proof for the lambda-calculus, where we prove the two semantics equivalent in the manner stated right here. So starting off with the lambda rule, the lambda abstraction rule, this is quite simple. Both the big step semantics and the CTS evaluate some heap and lambda abstraction to the same heap and lambda abstraction. So the proof is immediate in both directions. The application rule is a bit more complex, however, but still fairly simple. So if we start in the direction from big step to CTS, then first we assume that we have a big step transition for some application. And from that we can then infer that we must have transitions for the constituents E and E prime. Now, by using the induction hypothesis, which we have up here in the top, we can deduce that we must have equivalent CTS transition sequences that describe the same evaluation for E and E prime. So far, so good. Next, we can use the compositionality of computation trees to essentially wrap these two sequences, sec1 and sec2, in the application of the clause app1 and app2 from the CTS rule for application. We can do this because we have proof that E terminates and E prime terminates, and they must still terminate even if they are a subcomputation of some bigger computation. And at this point, we can just chain these transition sequences together to produce a full transition sequence for the evaluation of this application. In the opposite direction, going from CTS to big step, we just do the exact same thing in the opposite order. Break down the full transition sequence into sec1 and sec2, use the inverted induction hypothesis to get the premises of the big step transition, and then finally prove that big step transition. Yes. So up to this point, you have seen how we can use these rules to compute the value of an expression. But CTS captures the algorithmic aspects of inference rules in general. So we can also use CTS to describe how to compute the type of an expression. And so here we can see a simple example where I have added booleans and where we have a simple language with booleans, numbers, and addition. And the type rule for addition tells us to evaluate the type of E1, of E2, and we memorize both of these, but only if the resulting types were both net will there be a well-defined step saying that E1 plus E2 has the type net. If either of the constituents had the type bool, there would be no well-defined step, and the expression would be ill-typed. Furthermore, we can also describe parallelism and non-deterministic choice with CTS. So parallelism can be described by having multiple judgments in a single clause, which translates into creating multiple branches in the computation tree, and there actually making an actual tree. But each branch in this tree has their own valid regex, so we could either evaluate S1 or S2 one step, and the steps could interleave arbitrarily. Next, non-deterministic choice can be described by simply having multiple enabled clauses. So if we start out with the empty secondary component, then OR1 and OR2 would both be enabled, and we could get the result of evaluating S1 or S2, but not both. So what you have seen is computation-tree semantics, wherein we capture the big and small step aspects of a semantics, and the key data structure that enables this is the computation tree. We show that we can do a straightforward conversion from big step rules to CTS rules, and through that obtain a small step understanding of a big step semantics. We have also proved that for the 3 cases that we've covered, that the resulting CTS is equivalent with the original big step semantics, and we've also shown you how CTS can capture other kinds of capture relations other than operational semantics or transition relations. In the future, we would like to make this systematic conversion approach into an actual algorithm, so we don't need to do it by hand. And also, we'd like to improve support for concurrency in CTS. So I didn't mention it earlier, but CTS is restricted currently in the sense that the branch for S1, seen right over here, cannot actually affect the sigma stored in S2. So in the future, we would like to add some kind of shared state to CTS. Next, we'd also like to be able to obtain algorithms or even implementations from a computation tree semantics, possibly in combination with a concrete program in the semantics described. Finally, since we can describe both type relations and transition relations with CTS, we'd also like to prove soundness, to prove that a static semantics is sound with respect to a dynamic semantics, where both of them are described in CTS. And as you'll see in an upcoming work, this can actually be done in a quite straightforward manner. So that was all from me. Thank you very much.
Thank you. We have time for a few questions.
Hi, great talk. Really enjoyed it.
Thank you.
This might be more of a basic question, but is it fair to sort of understand the CTS data structure as a way of enforcing an evaluation order for big step operational semantics?
Well, they do encode continuations, so and you can see the possible orders in which operations can be evaluated from it. So I guess that would be a valid way of interpreting it. So so yes, like to evaluate x plus 3, yes, you can see it. To evaluate x plus 3, we must first evaluate 3. And this is, of course, at a point after we have evaluated x. So definitely, the computation tree encodes the order in which operations should be executed. But a big part of that ordering is also encoded in the rules in the CTS rules.
Awesome. Yeah. Thank you.
I think combined calculus needs a kind of special treatment in evaluation context. Can you Can you describe the semantics of call by need calculus in terms of yours?
Sorry,
Call by need calculus.
I cannot hear it, sorry.
No, maybe. Call by need calculus. Need.
Yeah, call by need and then...
Calculus. Can you?
Oh, calculus, sorry. Sorry. So now that I know what do you want me to explain? Just
you write CBN. Is it call by need or call by name? CBN.
Okay, yeah, that's the call by need.
Call by need. Oh, so you have already done it. Okay.
Yes.
Oh, okay. Okay. So, did you have any problem in describing that kind of thing?
No, there weren't that much of a problem with converting the big step semantics into CTS. So yeah, we have the example of application. So the primary challenge in this conversion is the data flow analysis, essentially, and establishing the order of premises. So the addition rule didn't have any strict ordering, but here, since we have a dependency between the two premises, then we of course also have an ordering in the big step semantics. And when we then convert it into a CTS rule, then the primary concern is to ensure that the data flow is retained. And yeah, that is where the primary component retains like the current state that we're evaluating in. So yeah, the biggest challenge there would be to ensure that we always have the latest state in the primary component. And of course, automating that conversion would also be a challenge, but definitely doable since we have data flow analysis. There's a question there.
Yeah, thanks, Kristian. So the big step semantics has an advantage. I mean, you're alluding to it at the end of making sure to capture what's independent of each other, which sub-computations. So, for example, in linear logic or linear lambda-calculus, you could say, like, I'm computing this part with only this environment, and I'm computing the second argument expression with another environment, and expressing that I don't need, I will not touch the first environment in the second one.
Yes.
Can you capture that? I mean, at some point, capture this kind of independence of evaluation order, and also the independence of other parts for computations, in this case, the environments?
Yes, the independence of evaluation order, not so much, because, well, you could evaluate them in parallel, but then you would need to bother with the consequences of two parallel parts of the program, which could complicate proofs. It's like opposed to in a normal big step semantics where you can either take the first case first or the second case first. So since CTS imposes a very strict evaluation order, it's not so easy to capture this independence. But the independence of program parts can definitely be captured. So in this example here, we evaluate S1 and S2 in the same in the same context, but we could evaluate them in different contexts. So you could evaluate them in different contexts, and we would be able to reason that, okay, they have different contexts, they don't touch each other. And in the sequential case, then you only have one branch at a time, so only that active branch could affect anything. So in that case, we can also show independence there.
Okay, thanks, Sean.